Okay, so this is a continuation, or more of an appendix to the last video that I did where we talked about the squeeze theorem. I did several examples of the squeeze theorem, but then I said that the squeeze theorem can actually be used to actually prove this limit, which becomes sort of an identity for us early on in our workings, and of course is validated later by other means. But what we can do is we can actually use this as an excuse to sort of work out the squeeze theorem in a little bit more robust way. This is kind of a neat little proof, and for those of you that want to watch it, and I'm proud of both of you, so let's go ahead and get started. Now, ultimately what I need to do is I need to wind up with cosine x, sine x over x, and I need to basically squeeze sine x over x between cosine x and 1, okay? Now, if you're wondering what that looks like, let's go ahead and delete these from the last one. If you have cosine is the cosine of x, y is equal to cosine of x, and let's zoom out just a little bit, and I know that I have y is equal to 1. I know that both of those, as x goes to 0, are going to 1. Now I can look at it graphically and confirm my suspicions that, sine x over x, and it actually does wind up sort of going between there and squeezing between cosine x and y is equal to 1 on the interval that I'm really worried about. But analytically, how do I work that out? Well, I'm so glad you asked, because it actually requires just a little bit of geometry, okay? And we'll just deal with it on the positive side here between 0 and pi over 2, okay? Now, if I have an angle measurement, which we'll call x, let's go ahead and draw a few lines in here, as geometry teachers do, and the students are always perplexed as to why the geometry teacher knows how to do that. It's pure magic. Trade secrets, my friends. I can't divulge. We're in constant contact with they. That mysterious they that writes the questions, like when the teacher gets up and says, what do they want when they ask you to do this? Now, if I have x right here, and let's go ahead and label a few of these points. Let's call the origin A. Let's call this B. And let's call this C. Okay? Now, if this is the unit circle, okay, and we'll call this D, and we'll call this up here E, okay? And it doesn't really matter what you call them. You can call them Q, whatever you want, okay? Now, I know that if this is the unit circle, right, I know that this BC line right here is sine x, right? That's sine x. So if I wanted the area of triangle A, B, D, I know that it's going to be 1/2 the base. Well, if this is the unit circle, then this AD right here is 1 unit. 1/2 base times the height, which is sine x. So we know that that area is sine x over 2. Is everybody with me? Now, let's go ahead and let's try and figure out the area of the sector ABD, because if I find out the area of the sector, I basically am going to be adding this little sliver right here to the area of the triangle, okay? Now the area of the sector is actually the angle measurement over 2, okay? As long as the angle measurement is in radians. Now, for those of you who are kind of like, how did you know that? Now remember that the area of a circle is equal to pi r squared. Now that is for the whole circle. The area for a whole circle, which includes 2 pi radians, is pi r squared. So let's go ahead and rewrite that as 2 pi over 2 times r squared. Okay, 2 pi representing the number of radians in a full revolution, and r squared, of course, being the radius squared. Well, if we're dealing with less than a full revolution, then that 2 pi becomes theta, and in the unit circle, that r squared becomes 1 squared. Okay, so that just becomes theta over 2. So the area of a sector is always theta measured in radians divided by 2. Okay, now here's the next question. If I wanted to find the area of triangle AED, okay, from here up to here down to here, which is larger than both of those, I need to find a measurement for ED. Okay, now notice that ABC is similar to AED. And so if I can find this, which I know from back in the unit circle times is cosine, sorry, not theta, but x, I know that I can set up a proportion. Sine x is to cosine x as ED is to AD, right? So sine x is to cosine x as ED is to AD. Well, I know that AD is 1, and therefore ED is equal to tangent x, right? Okay, well, I know the base. The base is AD. It's equal to 1. I now know the height. It's ED. It's equal to tangent x. So 1/2 base times height is tangent x over 2. Now, is everybody with me? Okay. Now here's what we need to do. We need to go ahead and set up a three-part inequality saying that the area of ABD is less than or equal to the area of the sector ABD, which is less than or equal to the area of AED. Or sine x over 2 is less than or equal to x over 2, which is less than or equal to tangent x over 2. Now, let's go ahead and multiply through by 2. That cleans it up just a little bit. And I get sine x, which is less than or equal to x, which is less than or equal to tangent x. Now, from 0 to 2 pi, sine is positive. And remember, we're dealing with that interval only. So from 0 to 2 pi, sine x is positive. So can I divide through by sine x? Yeah, it's perfectly legitimate, and that way I don't have to flip the signs. And I get 1 is less than or equal to x over sine x, which is less than or equal to, well, what is that? Anybody? Anybody? Well, if this is sine over cosine, and this is sine over 1, then this winds up being what? Okay? If this is sine x over cosine x, then to divide by sine x would just give you 1 over cosine x. Okay? Now, what can I do here? Can I reciprocalize all three of them? Sure, but when I reciprocalize, I need to swap the order and turn it into cosine x is less than or equal to sine x over x, which is less than or equal to 1, which is exactly the three-part inequality that I was counting on. So if I know that the limit as x approaches 0 of cosine x is equal to the limit as x approaches 0 of 1, and that's 1, then the function that has been squeezed between the two of them has to have exactly the same limit. And it is there. I have therefore proven that that is the limit of sine x over x as x approaches 0. Isn't that just handy dandy?